Hello dear all students. Today we are going to learn about the concept of steady flow energy equation, which is often termed as the SFEE. Steady flow energy equation is very much important topic from the engineering thermodynamics point of view as well as the fluid mechanics point of view. Steady flow energy equation is generally applicable to the open system, which describes the total energy flows of the system. So let us first discuss about the what exactly the steady flow is and the steady flow process is. Steady flow is defined as the rate at which the fluid flows through a machine or apparatus is remains constant. This type of flow is called as a steady flow. As we have already said that the steady flow process is generally applicable to the open system. So let us take an example of open system in which the fluid is entering into the system at one end and the same fluid is leaving out of the system at the other end. This means that all the thermodynamic properties associated with the fluid flow should not vary with respect to time. Then and then we can say that the flow process is the steady flow process. In fact, we can say that the total mass of the fluid entering into the system should be equal to the total mass of the fluid leaving out of the system, or the total amount of energy flow into the system that should be equal to the total amount of energy flow out of the system. When we consider the steady flow process for an open system, we have to assume a certain things. So the assumptions are, the first assumption is the mass flow through the system should remains constant. This means that the amount of mass entering into the system should be equal to the amount of mass leaving out of the system. The second assumption is the fluid is uniform in composition. This means that there should not be any suspended particle that will affect the fluid flow movement from one location to the another location. This means the fluid should be uniform in composition. The third assumption is the only interaction between the system and surrounding are work and heat transfer. Means no other effect other than work transfer and heat transfer should be observed during the fluid flow movement. The fourth assumption is the state of the fluid at any point remains constant with the time. Means all the thermodynamic properties of the fluid at any instant of the time should not vary with respect to time. In the analysis of thermodynamic system, only the potential energy, kinetic energy, internal energy, flow energy, heat and work transfer are to be considered while analyzing the system under the steady flow process. To write the steady flow energy equation for an open system, let us take an example. Have an open system schematic flow process for an open system. We know that the open system is one in which both the mass and energy may cross the boundary of the system. So we have taken a certain quantity of a volume under the consideration for the thermodynamic analysis purpose. That volume is termed as the control volume, and the boundary which surrounds that control volume is called as the control surface. We know that the for an open system there is one inlet and there is one outlet. So let the properties of the fluid entering at the inlet are P1, V1, U1 and C1, and the properties of fluid leaving the system at section 2.2 are P2, V2, U2 and C2, where P is nothing but the pressure of the fluid in terms of Newton per meter square, Pascal or bar. V is nothing but the specific volume of the fluid in terms of meter cube per kg. Product of pressure and volume is called as the flow work, which is defined as the amount of energy required to push a 1 kg of fluid in terms of kilojoule per kg. U is nothing but the internal energy per kg of the fluid in terms of kilojoule per kg. C is nothing but the velocity of the fluid in terms of meter per second. and Z is nothing but the height above the datum. Datum is called as the reference plane or the ground surface over which the system is kept. Here the Q is nothing but the amount of heat supplied to the system, and W is nothing but the work done by the system. Means to analyze the open system under the steady flow process, there will be an interchange of chemical energy in the fuel, kinetic energy of the moving particles, internal energy of the gas, and heat transfer, and the shaft work within the system is to be considered while writing the steady flow energy equation for an open system. Means by considering all the energy flows into the system and out of the system, we can broadly write the steady flow energy equation as energy flow into the system plus flow work plus the rate of heat addition, and this should be equal to energy flow out of the system plus flow work plus net work done by the system. Means what are the different types of energy flow into the system? Means we have to consider the internal energy of the fluid as well as the kinetic energy associated with the fluid, potential energy associated with the fluid, plus this flow work is nothing but the product of pressure and volume and the amount of heat supplied to the system, that is Q, and this should be equal to the energy flow out of the system plus flow work and the net work done by the system, that is W. With the help of this steady flow energy equation, we can write or we can derive the steady flow energy equation by considering this open system. As an example, the steady flow equation can be expressed as follows. For 1 kg of fluid, U1, the internal energy of the fluid entering at section 1 plus flow work, that is product of pressure and volume at section 1 plus potential energy of the fluid at height Z1, that is Z1 into G, plus kinetic energy of the fluid entering at section 1 that is C1 square by 2 plus or minus Q. Here why plus or minus? According to the sign convention, we know that when the heat is to be supplied to the system, then sign will be positive. When heat is rejected from the system, then sign will be negative. And this should be equal to U2, that is the internal energy of the fluid leaving the system, plus flow work, that is product of pressure and volume leaving the system, then potential energy, that is Z2G, plus kinetic energy C2 square by 2 plus or minus W. Again, according to sign convention, we know that the work done by the system is positive and work is to be done on the system is considered as negative. By rearranging the terms from this equation, we can write this equation as like this: U1 plus P1 V1 in one bracket plus C1 square by 2 plus Z1G plus Q. Why here is plus? Because in this case the heat is added to the system. This equal to U2 plus P2 V2 in one bracket plus C2 square by 2 plus Z2G plus W. Again here the plus sign, because in this case work is done on the by the system, that's why the sign is positive. Now we know that this U1 plus P1 V1 is nothing but the enthalpy, right? Means by replacing the value of U1 plus P1 V1 as H1, right? Plus this C1 square by 2 as it is, plus Z1G as it is, plus Q is equal to H2. Again replacing the value of this U2 plus P2 V2 as H2, plus C2 square by 2 as it is, plus Z2G plus W. By neglecting the values of Z1 and Z2, means by considering the system is kept on the datum surface or ground surface, we can neglect the value of Z1 and Z2 as equal to 0. So this can be reduced to H1 plus C1 square by 2 plus Q is equal to H2 plus C2 square by 2 plus W. So this is called the steady flow energy equation applicable to open system by considering the mass of 1 kg of the fluid. If the mass of m kg of the fluid, so this equation can be again written as like this. The energy equation for m kg of the fluid for steady flow system is given as follows. Yes, we have to just multiply the steady flow energy equation, general steady flow energy equation, by the mass of fluid, that is m. Now keep this in mind. Q and W. Q is nothing but the amount of heat supplied to the system, and this amount of heat supplied to the system is always per kg of the fluid, and the work done by the system is always per kg of the fluid. Means there is no need to multiply the mass of a fluid to this Q and this W, right? This equation can also be written as like this. Q is equal to, by shifting this whole bracket m into this bracket to the right hand side of the equation, and by taking m as a common, we can write u2 minus u1 plus z2g minus z1g plus this c2 square by 2 minus c1 square by 2 plus p2 v2 minus this p1 v1 plus w. Now we know that m into u2 minus u1 is nothing but the change in internal energy, that is delta U. Delta U is equal to m into u2 minus u1. Again, m into this z2g minus z1g is nothing but the change in potential energy. So change in potential energy is equal to m into g in bracket z2 minus z1. Again, m into this c2 square by 2 minus c1 square by 2. This is nothing but the change in the kinetic energy. So delta K is equal to m into c2 square by c2 square minus c1 square by 2. Again, m into this p2 v2 minus p1 v1 is nothing but the change in flow work at section 2 and section 1. So by replacing the value of this in the Q1 equation, again this equation can be written as like this. Q is equal to delta U plus delta PE plus delta KE plus delta PV, that is flow work, plus W. Again this equation can be written as like this. By shifting only this delta U to the left hand side of the equation, and we can write this equation: Q minus delta U is equal to delta PE plus delta KE plus delta PV plus W. So this is how we can write the general steady flow energy equation for mass of m kg of a fluid for an open system. With the help of this steady flow energy equation, we can write the steady flow energy equation for the number of engineering devices such as the water pump, water turbine, steam turbine, gas turbine, compressor, boiler, condenser, or nozzle. Now this is how we can derive the steady flow energy equation for open system. I hope you have understand the concept of steady flow energy equation. Thank you for watching this video.